The increasing use of high-strength materials in the sheet metal forming industry has introduced new challenges in this sector. The development of new materials, the application of new forming processes, but also the need for new testing methodologies. FormPlanet addresses this topic, the need for obtaining the crucial material properties to understand sheet formability and to predict part performance in service.
Competitiveness FHT contributed to the FormPlanet project with the development and performing of special materials characterization methods. We dealt with dynamic testing of components, we did characterization of their local properties, and we performed complex formability tests using the Nakashima method or cruciform specimens. We have developed complex testing methods to be used for materials characterization in high-demand industries.
We developed a new test for frictionless determination of forming limits of sheet materials under higher temperature. The second part of the Fraunhofer IWU was the introduction and investigation of in-process inspection methods within sheet metal forming process. We introduced material inflow sensors and several microstructure sensors into hot forming processes and cold forming processes in combination with artificial intelligence methods. We could show that these inline inspection methods will lead to a shorter development time, to better process understanding, and to zero defect production.
We've had the opportunity of developing new advanced and cost-effective testing methodologies to characterize formability and fracture resistance of high-performance sheet materials. These methodologies have proved to be effective to improve sheet metal part performance prediction and to reduce production losses caused by unexpected fractures in serial production, which represents a great advantage with respect to state-of-the-art testing methods.
LTU has contributed to the FormPlanet by developing advanced experimental methods to evaluate crashworthiness of car safety parts. LTU has also established experimental methods and efficient numerical methods to characterize and to model lightweight sandwich materials with high formability.
We have developed new material models for predicting the hydrogen diffusion and damage in high-strength steels, and we have worked on a new test method for the mechanical characterization of sheet metal containing hydrogen.
Atomic improved its own patent alias for OptPro, an innovative instrument to perform hydrogen isometal sheet metal components. Using alias for OptPro directly online during the part manufacturing, anomalies can be readily identified to reduce the risk for hydrogen agreement failures. The device was validated through industrial case studies, and with the collaboration of the Spanish Association for Standardization UNE, a STAND workshop agreement based on the novel methodology was published.
A+ Laboratories has performed a methodology inside FormPlanet project in order to qualify the quality of the different laboratories with a remote methodology. This methodology has been validated through several audits to some laboratories inside FormPlanet network. At the end of the project, this methodology validated can be used to qualify the performance of the laboratories of the FormPlanet testbed.
A wealth of materials information has come out of this project, including groundbreaking work in materials and experimental techniques and modeling. Our role was to bring together the scientific and engineering information in one place and deliver an effective materials information management system to the project and for its future business model. Together, we translated materials data coming from novel characterization techniques into datasets ready for use in digitalized formats and softwares that complies with fair data management principles, which is making sure the data is findable, accessible, interoperable, and reusable.
We have been the link between the project and the standardization system, making possible the consensus and the agreement among the FormPlanet partners and other European organizations to develop and publish two standards, chosen workshop agreements that will help the implementation of the test bed services and will assure their quality.
The advanced testing methodologies and modeling approaches developed and optimized in the FormPlanet project for the sheet metal forming industry has been validated by the industrial partners with 12 demonstrators from different sectors: automotive, home appliances, and packaging, and also with the different materials: advanced high-strength steels, aluminum alloys, multi-layer materials, cold-rolled steels, and stainless steels.
Two advanced testing methodologies have been validated on two particular case studies. In the first one, the local mechanical properties of small cosmetic packaging pieces were evaluated by using microtensile test methods. The second case study allowed to predict edge cracking issues in 5754 alloy by using the FormPlanet methodology that allows the determination of the fracture toughness via essential work of fracture technique. Both tests provide a simpler and faster experimental way to understand local properties and cracking behavior of the metal during forming, thus reducing products development costs and time.
The participation of Arania in the FormPlanet project has been focused in two different case studies. The first one was related to the drawability and the influence of the skin pass percentage reduction ranges on this property. The second study case was focused on the different behavior of the C45 steel grade in the fine blanking process, where materials with similar standard characterization in terms of mechanical and microstructure tests behave in a different way in the fine blanking process. Arania has been able to validate product and process parameters in a safety way than with the standard tests industrially available.
Our first goal was to supply materials to all the partners: 3 steel grades for cold forming and 2 steel grades for hot forming application. On the other hand, the objective of our case study was to compare the result of our classical crash test done in our lab to the test done by novel testing methodologies. A good correlation was found between results concerning absorbed energy during axial impact resistant test.
We worked with the Lulu Technical University, Eurocad. We produce the product, we make a tool design, make a prototype stamping, and make a series stamping of the product in order to see that the repeatability of the production exists. At the same time, this is very important to see that the product fulfills the end user requirements according the performance test procedure which is dedicated to the end user. In our case, we have the CRF as an end user, as a third party, in order to validate the product after forming. And they could see that the material has a good elongation and after forming, and this is repeatable. All those things make us very convenient to introduce our material to market by be a part of this project FormPlanet.
APNT's task in the FormPlanet project has been to conduct practical forming trials of a car dooring made of hot-formed high-strength aluminum. By implementing press output data from the practical trials into a FEM model, the goal was to construct a viable material card. A feasible and accurate way of conducting experimental tests for the tensile properties at elevated temperatures were found, and could be extrapolated to flow curves that were implemented in the material card. The material card for the aluminum alloys can be used in future studies about springback and virtual tool compensation.
The use of FormPlanet advanced methodologies allowed the company to determine potential cracking in an early stage by KI simulations. For that, STAMP has created a more confident KI library by correlation observed between a real test for FLC prediction Nakajima test and analytical FLC creations based on how they use. That allows to reduce cost during an early development phase and reduce rejected materials during production.
We stamped the upper side of B-pillar component using a different kind of material, from third generation steel to 5000, 6000 and sandwich sheet aluminum. The goal was to compare the virtual simulation and physical tests and see if using the advanced models, which take care about the toughness of the material, was possible to predict the edge cracking better than the current available models. The results were extremely positive. The new model converged faster than the traditional one, and the simulation is near to the real stamping.